Hello, today we are doing section 4.6. In this, we are going to learn about applications of exponential functions and logarithmic functions. First, I'm continuing from our equations. So we have these application kind of equations to solve. The first one is P is equal to 100 e raised to power kx minus 100, and it is asked solve for x. That means we have to find x in the terms of other variables. So what would you do? You will try to isolate the term containing x. So I would add 100 on both sides. That would give me 100 e raised to power kx is equal to p plus 100. I want to get rid of this 100, so I'm going to divide both sides by 100. That is going to give us e raised to power kx is equal to p plus 100 divided by 100. Now here we have an exponential equation kind of. We need to find x. X is our unknown here. So for isolating x, we will be taking natural log on both sides. That would get us natural log of e raised to power kx is equal to natural log of this whole expression, e plus 100 divided by 100. Now we know that natural log and exponential e are inverse function of each other, so they cancel. So we are left with only kx is equal to natural log of p plus 100 by 100. We need to find x, so we are going to divide both sides by k. So we have x is equal to 1 by k natural log of p plus 100 divided by 100. That would be your answer to the problem. Let's look at part B. It's an astronomy problem. Given L is equal to 8.8 plus 5.51 log D, solve for D. So we need to find D. So that means we need to isolate the term containing D. I'm going to subtract 8.8 on both sides. That is going to get me 5.1 times log of D would be left on one side. Other side would be L minus 8.8. We need to get rid of 5.1. We can divide both sides by 5.1. So we have log of D is equal to L minus 8.8 divided by 5.1. Now whatever this expression is equal to log of D, it's common log. Common log, if it is written, we had to assume that the base is 10. So by definition of log, we can say 10 raised to power this whole expression on the right hand side should be equal to D. So this whole side is the exponent, right? So by log's definition, we have D is equal to 10 raised to power this whole expression, L minus 8.8 divided by 5.1. That is using the definition of log, because the base here was 10. So base in the exponential also becomes 10. So 10 should be raised to this right side to get D. Next we have creating models for exponential growth and decay. So application problems for exponential functions. Suppose y is a variable changing exponentially with respect to t. Most of the problems t would be considered time, but it can be a different thing. Y naught, though, always represents the initial value of the y variable when time is 0. Initial means when we are starting to observe the problem, when we are starting to survey about the problem, or whenever we are starting to research about the problem. At that time should be considered 0. At that time, what is the value of your variable would be called y naught. Okay, so for positive constant k, if k is constant and it's a positive number, then the model y is equal to y naught times ekt is used as an exponential growth model, because that means it is going to grow, exponentially grow if k is positive. On the other hand, if we're talking about a decay problem, then we're going to consider k to be a negative constant. Let's see what we mean by following examples. Suppose that 15,000 is invested at the end of 3 years. The value of the account is 19,356.92 cents. Use the model A amount is equal to principal times e raised to power r t to determine the average rate of return under continuous compounding. So for continuous compounding, we know that amount is equal to, given by this formula, where P is principal, which is given to be 15,000 in this case because we are depositing $50,000. T is time in years. In this case, it's given to be 3 years. R is the unknown. Okay, and the final amount at the end of those 3 years is this number. So we have all these things. Let's put them all in the formula. We would get this is equal to 15,000 times e raised to power 3 r. R is unknown. So we need to find r. That means we need to isolate the terms with the r in it. So we're going to divide both sides by 15,000. Use our calculators. So we have e raised to power 3r is equal to 1.29 approximately. Now our goal is to find r. That means we need to get rid of exponential equation, right? So what do? We are gonna take natural log on both sides. So what will we have? Natural log of e raised to power 3r is equal to natural log of 1.29. Now natural log and exponential are inverse function of each other, so they cancel. We are going to be left with only 3r, which is equal to natural log of 1.29. R would be equal to natural log of 1.29 divided by, let's calculate that, natural log of this divided by 3. We have 0.084. So this expression is, now R came out to be 0.084. That is a decimal number. In percentage, R would be 8.4% interest. So how much interest rate they are getting for that 3 years? 8.4% using the given formula. Let's consider another problem. Creating a model, exponential model for population growth. So it's a growth function. So remember, in the exponential function, the power has to be positive. On January 1st, 2000, the population of California was approximately 34 million. On January 1st, 2010, the population was 37.3 million. Write a function in the form of pt. P at t is given to be p naught e raised to power kt to represent the population of California in millions t years after January 1, 2000. So t is number of years since January 1st, 2000. Round k to 5 decimal places. Now, what do we have here? in this kind of function, I told you when you are starting, when are we starting? On January 1st, 2000. On January 1st, 2000, t would be 0. So the population will become P naught. So P naught is initial population at time t to be 0. So what is given? Initial population in year 2000 is given to be 34 million. So this answer is in millions. You don't have to write it with zeros. Okay. Now in 2010, in January 1st, 2010, how many years it's been since 2000? That is 10. So T is number of years since January 1st, 2000. That would be 10 years. So T is 10. So population at T10 will be calculated P naught times e raised to power k times 10. And we are given that on January 1st, 2010, the population is given to be 37.3 million. So what we are saying, P naught we already found to be 34. So we are saying that 34 times e raised to power 10k is equal to 37.3. We need to figure out what is k. Okay. So I need to isolate the term containing k. I'm going to divide both sides by 34. Let's use the calculator. So we have 37.3 divided by 34, 1.09. So we are saying e raised to power 10k is equal to 1.097, something like that. We need to find k. So we're gonna do what? We are gonna take natural log on both sides because the base is e. It's better to take natural log. So we have natural log of exponential function e raised to power 10k is equal to natural log of 1.097. Now, natural log and exponential function, they cancel each other if the base is same, which is e. So what we are left with is 10k. 10k is equal to natural log of 1.097. K is equal to natural log of 1.097 divided by 10. So we can calculate natural log of this number divided by 10. So we have 0.00926 for the 5 digits, that is k. Now let's go back to the problem. Use the function in part A to predict the population in 2080. So before, write the function in that form. So we need to figure out this function, right? In general, the exponential function population is written as P naught. P naught is 34 times e raised to power k. Now we found k as this number times t. So this is our exponential growth function, which represents population in t number of years since January 1st, 2000. Now the question is to predict what will be the population in 2018. In 2018, t is equal to 18. So for part B, population we have to calculate P of 18 using our formula which we already found, 34 times e raised to power 0.00926 times 18. So we can calculate that. $40.17 million. So in 2018, that would be your population.